Hey guys, so let's take a look at our last chapter for the semester, chapter 11 on organohalides. No, it is chapter 10, I beg your pardon. Okay, not that really matters. Organohalides, which introduces us to some radical reactions, which we haven't really seen so far this semester, other than that tiny little bit we did in the alkenes chapter for polymers. So it's a bit of a weird one with the organohalides, or haloalkanes as they're sometimes known, just alkanes with a halogen attached. They're sometimes given their own separate functionality, but really they're the paupers when it comes to functionalities. They're the lowest denomination in the pack. So they're only one very small step above alkanes themselves in terms of functionality. So we can have haloalkanes, we've got a halogen attached to an alkane chain. We sometimes talk about haloarenes when we've got a halogen attached to an aromatic ring compound of some kind, usually a halogen bonded to a benzene derivative, a six-membered ring of alternating double and single carbon bonds. So that halogen, when present, doesn't change how we name the molecule. We really just follow what we learned in the alkanes chapter, and we don't give any special deference to the halogen atom when it's present. So just as we did with the alkanes, we're looking for the longest continuous chain of carbons, and we'll number that main chain to make the first branch the lowest possible number. And we don't care whether it's a halogen or some kind of alkyl group. So the presence of the halogen doesn't actually do anything to the nomenclature, the naming of the compound. So because we can number from the left and you see a branch on carbon number 2, that's more important than the fact that the chlorine, which would be on carbon number 5, would be in theory more lowly numbered if we numbered from the right, 1, 2, 3, 4. That's not going to count in this case, because that means that our first branch is on carbon 4 instead of on carbon 2 as we number from the left. So we don't give special deference to the halogen that's present. It's really just nomenclature that we first learned with the alkanes back at the beginning of the semester. Likewise, if we have got a tie between numbering on the left or numbering on the right, then we give preference to alphabetical ordering. So we go B for bromo and number from the left, rather than M for methyl and numbering from the right. Remember, this is just a last resort if there's a tie between the positions of the branches on the two sides of the alkane chain. It's normally about the lowest possible numbering for those branches, whether they're alkyl branches or halogens. Let's clear up my screen. Okay. So if there's any other kind of functionality present, like a pi bond for an alkene or an alkyne, then that takes precedence. So with a double bond, it's really an alkene derivative, as we looked at before, or a triple bond, it'd be named as an alkyne derivative. When it comes to properties, because the carbon to halogen bond is going to be a polarized bond. So the haloalkanes are polar molecules, most of them with a dipole moment, because that dipole moment we've looked at in chapter 2 of the semester, when we're looking at that separation of charge between the protons in the nucleus and the electrons in the chemical bond. And we saw how to calculate that. In more basic terms, that polarity of the bond and polarity of the molecule depends on two main factors. You've got the difference in electronegativity between the atoms, and we said, remember, that a difference of 0.5 becomes significant. We also sometimes have to take into account the sheer size of the atoms. As the bond gets bigger because of bigger atoms, the bond becomes more polarizable, as the electrons are more removed from the influence of the protons in the nucleus. So if we look at the carbon to halogen bonds for all 4 of the halogens, we can see initially, as we go from fluorine, chlorine to bromine to iodine down the group, initially we see a rise in the dipole moment of the bond. That's because we're seeing an increase in the size of the atom. But we also see as we move down that that polarity starts to diminish towards the bottom of the group, even though the atom size is increasing. And working against that is a decreasing difference in the electronegativity between carbon and the halogen atom. So it's a bit of a choppy sea when it comes to the polarity of that bond, because we've got 2 different factors going on. The bond length is increasing as we move down the group, but the difference in electronegativity is decreasing as we move down the group. Okay. Boiling points, as you can imagine, we see higher boiling points for haloalkanes compared to alkanes because of the polarity of that bond, leading to dipole interactions, what we sometimes more generally describe as van der Waals forces. The electron-enriched part in one dipole bond, the halogen, stacking up onto the next molecule next to the electron-deficient part, the carbon atom in that carbon to halogen bond. That leads to stronger forces of attraction between the molecules and the higher melting temperatures and boiling temperatures compared to the alkanes. If we look at things like aldehydes or ketones or alcohols with more polarized bonds, they would have even higher melting and boiling temperatures. So for boiling point elevation and melting point elevation, the haloalkanes are only really better or higher than the alkanes themselves, which have no polarity. Now for this relatively short chapter, there's a couple of the reactions we want to look at. The first one is alkane halogenation, which is a reaction which is kick-started in the presence of light or high temperature. And it's actually the substitution reaction that we talked about right at the beginning of the semester in chapter 1 and 2, when we're looking at chapter 3, I beg your pardon, when we started looking at the alkanes. So an alkane like methane exposed to some halogen like chlorine with some UV light or some elevated temperatures, probably above 100 degrees Celsius, we can cause a substitution of one of the hydrogens for a halogen atom to give this haloalkane with a little bit of hydrogen chloride as a side product. Now, when we're doing these reactions, we're normally doing with either chlorine or bromine. We tend to find that attempting to do fluorine is way too exothermic, way too reactive. It's therefore difficult to control the reaction, and can sometimes, as I found out in my youth, can be explosive. And then with the iodine reaction, it's actually very difficult to get it to react because it's such an endothermic reaction. There's a lot of energy that has to be put in, so it's relatively unreactive. We usually get only a very small amount of product produced. So it's usually the middle ground of chlorine and bromine which undergoes this reaction. And the reaction is relatively regiospecific or regioselective. Certainly with bromine, which is more regioselective than chlorine, the substitution with bromine likes to be on the more substituted carbon. So with examples of a propane, I've got 2 terminal carbons, 2 methyl groups on either side, That's just a primary carbon because it's got one carbon neighbour. But then the carbon in the middle there, the apex, that has two carbon neighbours and is referred to as a secondary carbon. And that more substituted carbon in the middle, the secondary carbon, is the more common position for the substitution between the halogen and the hydrogen when we apply heat or light. So the major product would be 2-bromopropane, 92%, compared to either one of the two terminal carbons, which would produce 1-bromopropane, just 8%. Same again with bromine reacting with 2-methyl propane. We've got 1, 2, 3 primary carbons, but there's a tertiary carbon in the middle with 1, 2, 3 carbon neighbours, and that gives the higher yield. 95% of the 2-bromo, 2-methyl propane, and only about 5% of one of the 3 positions that would give 1-bromo, 2-methyl propane. Chlorine in the reaction isn't quite as selective, but it still leans towards being regioselective, choosing the more substituted carbon. So if we use, for example, 2-methyl butane, that second carbon with 1, 2, 3 carbon neighbours is certainly the preferred position, but not quite as extensively as it was with bromine, just 72% yield, and then the majority of the remaining yield going on that secondary carbon position. So pretty much almost no primary carbon substitution. And we see this normally for these haloalkane synthesis reactions. Tertiary is preferred to secondary, which is preferred to primary hydrogens. Now the reason for this is tied up into the mechanism of the reaction, and the reaction path follows a radical mechanism, meaning at some point in the reaction we have a carbon with an incomplete octet, specifically an unpaired electron in an atomic orbital. And so it leads to instability for that carbon, that radical carbon with the unpaired electron, because of its incomplete octet, but it's stabilized by hyperconjugation. The bonding electrons from neighboring carbon to hydrogen bonds overlapping with that incomplete atomic orbital, so it's getting a bit of the electron share from the CH bonds around it, and the more substituted carbon has more CH bonds surrounding it, so it's better stabilized. Now most of the reactions that we have looked at so far have been heterolytic reactions, which means that when the bonds break, both of the electrons in the bond normally head in one direction. They head to the more electronegative element, and that's led to cations and anions in our mechanisms. For our reactions today, we're looking at reactions, excuse me, just a little bit of acid indigestion, but you definitely didn't want to hear that. So usually we get these anions and cations, which lead to nucleophiles and electrophiles. But we're not seeing that in this chapter, because we're talking about non-polar chemical bonds breaking, like carbon to carbon bonds or oxygen to oxygen bonds. The bond breaks under radiation of light or at higher temperature, and the electrons in the bond go their separate ways. It's a tie. There's no difference in electronegativity, so the electrons in the bond are split between the two atoms when that bond cracks. And notice that the arrows we use have just half a head, representing the movement of just one of the two electrons. So we sometimes produce these methyl radicals with a carbon with an incomplete octet and an unpaired electron, or hydroxyl radicals with an oxygen with an incomplete octet and an unpaired electron in an atomic orbital. These are very reactive because they're looking to complete their octet. This is what we call homolytic bond cleavage, when the electrons go their separate ways when the bond breaks. It's normally because the bond itself was non-polar. Neither of the two atoms had the upper hand when the bond breaks. So the mechanism falls into 3 steps under irradiation of light or heat energy, as we talked about with the polymer synthesis in the alkene chapter, and it falls down into 3 steps: initiation, propagation, and termination. Initiation step is that initial production of the radical. So homolytic bond cleavage, something like bromine, breaking the bond to give us 2 bromine radicals. We only need a small amount of the radical to be produced, because you can see from the propagation step, the second part of the reaction, by the end of the 2-step process, we produce more radical. And that radical can be put back in to react more of the starting material. So it starts with one of the more substituted carbon atoms, as we said. Let's see, let's switch to red. And that carbon to hydrogen bond breaks. One of the electrons retreats back to the carbon, and one of the electrons combines with the radical bromine, taking the hydrogen with it. So we produce a small amount of hydrogen bromide, and we produce a propane radical in this case. Non-radical molecule reacting with a radical molecule will always produce a radical product, a molecule with an unpaired electron on one of the carbons. And so that propane radical then reacts in the second step, reacts with some of the pure bromine. So the electron is going to reach out for one of the bromine atoms, and that bromine to bromine bond breaks. As the bond breaks, one of the electrons retreats back to the far bromine, and one of the electrons, taking this bromine atom with it, combines with the electron from that radical carbon to produce a new carbon to bromine bond. A substitution with bromine by adding on the bromine and removing that hydrogen in the first step. One of the nice things about the propagation step for these reactions is that if you look at any chemical which appears on the left and the right over the 2 equations, you can cross them out to give you the overall reaction conditions. So we've got a bromide as a reactant in the first step, or a bromine radical I should say, and I've got a bromine radical on the right hand side in the second step. We've got the propane radical as a product in the first step and as a reactant in the first step. So we can emit them out, and it gives us our overall conditions. An alkane reacting with some bromine will produce some bromoalkane and some hydrogen bromide as our side product. So that's a good check to make sure that you're doing that 2-step propagation step properly. You can cross out the materials which appear on the 2 sides of the 2-step process, and it should leave you with the overall original reaction conditions. Okay, so this is the guts of the reaction, the propagation, and the reaction continues, repeating each step until the concentration of the original alkane starts to run out. Once it's depleted, the radical, quiet, my cat, sorry, the radical in the reaction statistically has less of a chance of bumping into an alkane and more of a chance of bumping into another radical fragment. You react a radical with a radical, you terminate the reaction. That can happen in several ways. It could be some of the radicalized alkane reacting with other radical alkane. Those lone pair electrons reach out and combine with each other to make a new carbon-to-carbon bond, and we extend the molecule with a little bit more side product, 2,3-dimethylbutane in this case. Or it could be we make a little bit more of the actual product itself, some radical alkane with some radical bromine to produce more of the actual product, or maybe some bromine combining with another bromine radical to produce the original bromine liquid. So initiation is we produce the radical. Propagation is that radical reacts with the supply of the reactant, the alkane, until that supply is exhausted, and then chain termination with a radical combining with a radical to produce a non-radical product. And once you produce a non-radical product, you terminate the reaction. There's sometimes something known as a disproportionation reaction that occurs, and that's with two radical alkane molecules during the propagation. Sometimes the carbon to hydrogen bond adjacent to that radical atom, that bond breaks as it collides and reacts with some other alkane radical. So the alkane radical on the left, it uses its electron, reaches out for the hydrogen. The hydrogen, that carbon to hydrogen bond breaks, and the hydrogen with one of the electrons combines with the radical alkane to produce a little bit more of the original alkane. And the second molecule, as that electron combines with the adjacent radical carbon electron, we form a little bit of alkene. This is sometimes seen in small proportions, like maybe 3 or 4%. This is what we sometimes call disproportionation. And that's it for our first of two reactions. Let's look at some more examples. Let's try ethane this time with bromine, irradiated with light. Again, the initiation is producing a radical, a bromine to bromine bond breaking to produce as some bromine radical. A bromine radical then reacts with the ethane in a two-step propagation process. The alkane, the CH bond that breaks, one of the electrons taking the hydrogen with it combines with one of the bromine radicals to produce some hydrogen bromide, and the remainder of the reactant, the propane itself, as one of the electrons retreats back to the carbon, it produces some ethane radical. That ethane radical in the second step then reacts with some of the initial bromine. It combines the electron with one of the electrons from the bromine to bromine bond, as that electron drags along the first bromine atom with it. So we make some bromoethane, and that second bromine atom, as the bond breaks, turns into a bromine radical. And so we replenish our supply to keep that propagation step going. It keeps going until we exhaust a supply of the starting material. And statistically, it starts to become more likely that a termination step will ensue as a radical molecule combines with another radical molecule. That could be two ethane molecules or ethane radicals from the propagation step to produce one big long butane molecule. It could be the ethane radical reacting with the bromine radical to produce a little bit more of the bromoethane product, or maybe just reproduce the original bromine. Again, two ethane radicals. Oh, excuse me. Let me take a drink. Somehow managed to spill that over myself. Two ethane radicals. First one with its lone electron combines with a neighboring hydrogen, and that bond breaks, one of the electrons dragging the hydrogen with it, as it forms a new bond to the first ethane radical. A second electron from the carbon to hydrogen bond combines with the neighbouring carbon radical electron. Sorry, my screen get messed up there. And we produce a carbon to carbon double bond and produce a small amount of ethene in that disproportionation. Keep in mind that the substitution reaction, quite often on a carbon that's more than substituted once, will produce a product which is chiral with 4 unique groups attached. So the reactions often produce technically 2 products, the R and the S stereoisomers. Let's look at another, this time looking at methane, the first alkane itself, reacting with bromine. Again, initiation, that bromine to bromine bond breaks under a high temperature or radiation from light. We produce those bromine radicals. One of them will react with a molecule of the starting reagent, the methane itself. The carbon to hydrogen bond breaks. One of the electrons retreats back to the carbon to produce some radical alkane. One of the electrons from the bond, dragging the hydrogen with it, combines with the lone electron in the bromine to make a new bromine to hydrogen bond, and we produce a little bit of hydrogen bromide. Second step, that alkane radical we produced reacts with some of the initial bromine. The bond breaks, the bromine to bromine bond. The electrons go their separate ways. One of the electrons, dragging one of the bromine atoms with it, combines with that unpaired electron to make a new bromine to carbon bond. And again, if we cross out the materials which appear on both sides over the 2-step reaction, cross them out and it gives us our overall reaction conditions. So cross out the bromide, the bromine radical on the 2 sides, cross out the alkane radical on the 2 sides, and we're left with the overall reaction conditions. The alkane reacting with bromine to produce the bromomethane, and we get some hydrogen bromide as a side product. If you can get to the overall reaction conditions by crossing out the chemicals which appear on both sides, then you've probably done the 2-step propagation reaction correctly. Again, once the concentration of the original reagent, the alkane, diminishes close to 0, it's becoming more likely that the radical will combine with another radical to produce a non-radical product and terminate the reaction. There could be some alkane radicals combining to produce an extended molecule of ethane, some alkane radical combining with the bromine radical to produce more of the major product, or 2 bromine radicals combining to form the original bromine reagent. Again, we also see that halogenation occurring with chlorine quite successfully. And the halogenation reaction often doesn't stop if you have high enough concentrations. So you can chlorinate or brominate once to give chloromethane, chlorinate twice to give dichloromethane, or chlorinate even a 3rd time to produce chloroform quite easily. So again, as we said, the more substituted carbon is going to produce a major product. We see that with butane reacting with chlorine to produce the 2-chlorobutane. That's a major product. But sometimes we don't see that more substituted carbon reacting. A good example of that is 2-methylpropane reacting with chlorine. The tertiary carbon only sees 35% product, while one of the three primary carbons sees 65%. And this is sometimes about just the sheer probability of the molecules colliding at that point. That tertiary carbon is sterically hindered, it's more difficult to hit, and statistically, you're 3 times more likely for the chlorine to collide with one of the 3 primary carbons. So sometimes it's about statistical fudging, changing the proportions of product that you expect. Again, we said that the bromine was a reaction that was more regioselective than the chlorine, and that's because the reaction with bromine is less spontaneous because of bond energies and the energy of the intermediate compared to the chlorine reaction. So the bromine reaction is more dependent on stabilization through hyperconjugation of the more substituted carbon. Chlorine reaction is more spontaneous. It doesn't rely on hyperconjugation for stability, so it's less fussy about where the substitution occurs. Tertiary radical, more stable than a secondary or a primary. So the bromine reaction with 2-methylpropane sticks to that more substituted product side. Right, a little bit more to go. The second of the 2 reactions we want to look at, to finish off the chapter, is the allylic halogenation reaction. Now we've seen alkenes react with bromine in the alkenes chapter 7. That was one of our early mechanisms where we had that 1,2 addition reaction across the double bond, and we produced a dibromo alkane of some form. However, if the reaction is carried out at a high temperature, or the reaction is carried out while irradiating with light, we see a very different mechanism for the reaction. We see this allylic substitution. And if we look at the carbons in the double bond, the 2 carbons in the double bond themselves are called vinylic carbons. And so any hydrogens attached are called vinylic hydrogens. The carbon which is adjacent to the double bond, sp3 hybridized, is what we call an allylic or allylic carbon, depending if you're British or American. The allylic carbon next door is where we see the substitution occurring if the reaction is carried out at high temperature or with the irradiation of light. Now, instead of using bromine, we tend to use a more specialized source for the bromine, and NBS, which is N-bromosuccinimide, quite commonly seen at a high temperature, 350 degrees, say. And so instead of that addition reaction, which you would normally see at room temperature, at high temperature or irradiation with light, we see this allylic substitution. Now the reasons for that are tied into the bond energy. If you look at the carbon to hydrogen bonds for one of the carbons in the double bond itself, the energy of that bond is quite high, 464 kilojoules per mole. But if we look at the energy for the carbon to hydrogen bonds in one of the adjacent carbons, the allylic carbon position, that bond energy comes down by almost 100 kilojoules per mole, down to 372. So at high temperature, when the molecules are whizzing about at high speed, the molecules have enough energy to break that allylic carbon to hydrogen bond. And so this is why we see a substitution reaction at high temperature rather than the addition reaction along the carbon to carbon double bond. Again, stability is important to the reaction. So an allylic substitution is actually more stable, more reactive than a tertiary which we said was better than secondary, which was better than primary. Now, the reason for that allylic substitution being more reactive and being a more stable radical is because we have the capacity for resonance. So if we look at an example, 4-methylcyclopentene reacting with the N-bromosuccinimide, NBS, light or heat energy will cause that nitrogen to bromine bond to break, produce some bromine radical, and instead of reaction by addition across the double bond, it's the adjacent allylic carbon which sees a substitution reaction instead of the addition reaction. Let's look at the mechanism for it. So step one, the initiation, of course, the nitrogen to bromine bond breaking to produce some bromine radical. That bromine radical is then thrown into the two-step propagation reaction. So with the alkene, again, it's the adjacent carbon to hydrogen bond, high temperature, that lower bond enthalpy, that's the bond that breaks as the bromine comes hurtling in. And so as the bond breaks, one of the electrons retreats back to the carbon to form that radical, and the other electron, taking the hydrogen with it, combines with the unpaired electron of the bromine radical to produce some hydrogen bromide. That allylic radical uses its electron to combine with one of the bromine atoms in a molecule of bromine. As that bromine to bromine bond breaks homolytically, one of the electrons retreating back to the other bromine as we produce another bromine radical fragment, and the other electron retreating back to the bromine, taking the bromine with it as we use those two unpaired electrons to make that new carbon to bromine bond and complete the substitution. Again, if we cross out the things which appear on each side of the two-step equation, so the bromine radical and the allylic radical, it gives us the overall conditions. The alkene reacting with some bromine overall to produce some bromoalkene and some hydrogen bromide. Again, eventually that initial alkene reagent is used up, so it becomes increasingly statistically more likely that some of the radical is going to combine with another radical to terminate the reaction. It could be some bromine radical with some bromine, or some bromine radical with the allylic radical to produce a little bit more of the product. And then occasionally some of the allylic radical reacting with more allylic radical to produce this big, bulky, extended product. Sometimes maybe 2 or 3% will be produced like this. Now for the N-bromosuccinimide itself that we had, overall it reacts with some of that hydrogen bromide that was produced, doing a switch between the bromine and the hydrogen. So we do produce some bromine that can be used in the propagation step. Now the greater reactivity and greater stability at high temperature through this allylic mechanism is because of the capacity for resonance. You've got the lone electron, unpaired electron on that allylic carbon, but then of course that's an sp2 hybridized carbon, like the sp2 hybridized carbons in the carbon-to-carbon double bond. So that unpaired electron can combine next door with one of the electrons from the pi bond to make a new pi bond next door, and the last electron retreats back to the end carbon to produce the radical on the other side of the double bond. And so this resonance gives greater stability, but it also allows for a mixture of products, depending on whether the bromine reacts on the carbon here or the carbon here. So we can sometimes get a rearranged product. So, oops, just get my pen working. So taking that alkane, remember next door, that first carbon, which is not part of the double bond, that's a allylic carbon with a much weaker carbon to hydrogen bond. So reacting with the N-bromosuccinimide, a bromine source, and carbon tetrachloride as solvent, it produces some allylic radical. Now the reaction with bromine could go straight on to produce the bromination in that allylic position, or more likely we could see resonance as that lone electron swings around, combines with one of the pi electron bond electrons to form a new double bond here. The second electron in the pi bond retreats back to the N carbon to produce some primary radical. Because that primary radical isn't normally stable, but it's stabilized through the resonance forms which are forming here. And that resonance allows the primary product to be the major product. So producing 1 bromo oct2-ene rather than 3 bromo oct1-ene. Again, we can see it here. The alkene, or the methylene cyclohexane, reacting with NBS, which is our bromine radical source, NCCl4, carbon tetrachloride as solvent. Nasty stuff, carbon tetrachloride, by the way, banned in many universities for being too toxic, too carcinogenic. So we initially produce some allylic radical. Here, that's a carbon adjacent to the double bond. But we see this rearrangement where that lone electron combines with one of the pi bond electrons to make a new carbon to carbon bond here, and the other electron in the bond retreats back to the N terminal carbon, and then the bromine attacks here to give us this primary brominated alkene. So again, if we look at the example, initiation to light or high temperature, causing that nitrogen to bromine bond to break in the N-bromosuccinimide, producing some bromine radical. That bromine radical collides with the carbon to hydrogen bond, that allylic bond, causing it to break. One of the electrons retreats to the carbon. One of the electrons, taking the hydrogen with it, combines with the bromine radical to produce some hydrogen bromide. And we do get some product bromination in this position, but it's resonance stabilized, so we get much more of that methyl radical produced. That's where the bromine more preferentially attacks. It's sterically less hindered, and that's our major product. Again, for termination, radical combining with radical in multiple ways to terminate the reaction. Okay, last reaction to just very briefly talk about, because we'll talk about it more in Chem 202 next semester, are Grignard reagents and Gilman reagents. One of the most important reactions for a chemist is being able to extend the carbon backbone. That means we need to be able to make new carbon to carbon bonds. One of the easiest ways to do that is to produce a Grignard reagent. This is where we have magnesium wedged in between a carbon and a halogen. fairly easy to produce overnight. You take some kind of bromoalkane in solid magnesium with ether as solvent, just stir it overnight. That magnesium pushes its way in between the carbon and the halogen to produce the alkyl magnesium bromide, or Grignard reagent as it's known. It works with alkanes, it works with aromatics. And the important part here is that carbon, now bonded to the metal magnesium, the carbon has the greater electronegativity. And so the electrons in that bond are polarized towards the carbon, making it electron enriched, and it gives the carbon nucleophilic nature. It gives us a carbon anion character, a carbon with a negative charge. You create a carbon with negative charge, you create the possibility for the organic to act as a nucleophile rather than the electrophile as normally happens. You can produce alkyl lithiums in a similar way. Take a bromoalkane with lithium in a alkane as solvent, something like pentane or hexane, which are liquid at room temperature. And again, the lithium bonds onto the carbon in the chain, knocking off the bromine this time, doesn't stay attached like the Grignard reagent. Because the carbon is more electronegative than the metal, the bond is polarized in favor of the carbon, and we produce carbon anion character. One of the most useful reactions for the alkyl lithiums is to produce Gilman reagents, which gives us much more controlled carbon backbone extensions. So that alkyl lithium you've produced, react it with copper iodide, you'll produce the Gilman reagent, which is an alkane with a copper lithium combination for the organometallic. That can then be very successfully reacted with a haloalkane, especially iodoalkanes. The alkane here, the dimethyl group, has carbon anion character because it's more electronegative than either the copper or the lithium. So it uses those electrons in the bond to attack the carbon to iodine carbon, which is electrophilic because the electrons are being drawn away by the more electronegative iodine. It's basically an SN2 substitution reaction. The alkane comes in, the halogen atom pops off. We can extend the carbon backbone, turning hexane into heptane. Benzene turned into toluene. Pent-1-ene turned into hepta-3-ene. And that was it. In terms of the preparation of the haloalkanes, industrially most common methods are to take alcohols of some form, react them in SOCl2, thionyl chloride, with pyridine as a little bit of base. And the alcohol group is substituted for a chlorine. Or if we want a bromine, we can take an alcohol and react with phosphorus tribromide and ether. The alcohol group is replaced with a bromine. I'll talk about Gilman reagents and Grignard reagents much more in Chem 202. That's it. That's all the new stuff left. And of course, the organohalides chapter itself will not appear in the final exam. That would have been too mean, even for me.